Thanks, Gavin. I'm glad to be here, and I appreciate that intro. And that's exactly what I'm here to do, is talk about how to harness the imaging and other GNSS innovations to take your survey efficiency and your ROI to the next level. So, like Gavin said, I'm Bob Kilburn, survey and engineering product manager for the US and Canada. I've been in the industry for 24 years. I started out as a Marine Corps field artillery observer. And then when I got out of the Marine Corps, I got into the engineering survey side. I've been with Leica Geosystems for 5 years now. I started out as the sales rep for Wisconsin territory, and then just in January, I took over this role. So briefly, we'll take a look at the past 35 years or so of GPS, just as a snapshot of where we've come from and where we potentially might be going, and some of the technologies that needed to come along so that we could add some of these features and increase the options for the user. So it's not just about the sensor. Sometimes it needs the satellite constellations, which take countries to build and develop, like GPS, but then it went on to be GLONASS, and then Galileo, and then QZSS, and all the other systems that are out there made it where we could develop things like RTK Plus, which is a self-learning GNSS antenna, because we got to a point where we had enough signal where we weren't just worried, is the signal to noise ratio low enough that we can accept it? Now we had a potential of having too many signals, or at least enough that we could start filtering out the good signals from the really good signals, or the acceptable signals that we would love to have. In 2006, now they were no longer needed to process when we come out with 2016 with the GS18. Then a couple of years later, and a year later, we come out with the GS18T, which is the tilt rover, fully immune to the magnetic disturbances because of the use of an IMU. Crazy fact there is that we couldn't find an IMU to buy at Hexagon or Leica Geosystems that was miniature enough, accurate enough, and in the right price range that we could sell it for a receiver. So it was a technology we had to develop in-house to put into the receiver to give us this capability. And that helps us. So that's who I am again. I'll quickly recap. This is the slide I was on, just talking about the different technologies, when they came about, and where we're at today, or how we got to where we are today. Just for a point of reference, 15 years ago, this is what a GPS sky plot would have looked like compared to what we have capable today, where we can get upwards of 29 satellites with all the constellations. So that really enables us to do a lot and to start filtering down. I remember the days when we planned we'll do total station in the morning and GPS in the afternoon, because we had better satellites then, and trying to track those and remember that they moved about 4 minutes a day. So in a couple of months, we would be tweaking our times of when we were doing different types of survey work. So the GS18T is the fastest GNSS rover. Once we came up with that IMU to correct, we no longer had to worry about leveling the rod to take every shot. Really changed the game of collecting survey data, especially your large topos. The fact that it wasn't reliant on a magnetic correction, the IMU being calibration free, just made it so much faster than anything else that was available before it. Here's a quick video just showing the power. You know, when you got to measure that 1 point or check that 1 point, was this run over? Was it not? This is a chore. You know, this becomes having the equipment there, getting operators to move it, the magnetic interference for everything else before that made this almost impossible. That was completely overcome with the GS18T. Other simple things that we take for granted are just the offsets. So getting those corner shots became something we didn't have to think about anymore. We didn't have to put in an offset. We didn't have to shoot a couple of points in Kogo to create the other ones and do offsets. We could just tilt the rod and take the measurement. Our customers came out with creative and challenging things that they had to overcome that we hadn't thought of. You know, the benchmarks on top of big, large cut areas that were driven and set, and just checking those. That's something that couldn't be done or wouldn't be done. You'd have been setting up a robot and shooting that with a prism to make those checks. Well, now with the tilt rod, we could overcome that. The GS18T shooting inside of the culverts and stuff like that was, again, something that we've been dealing with for a long time as surveyors. Everybody on here that has surveyed in the past is familiar with these challenges. And they're not something that's not insurmountable, but it does take time, it does take effort, and it does cost money. It introduces another chance of adding human error, which is just all the things we want to remove. The guys are out there, they're in the heat, they're in the sun, they're working really long days. So any chance we can remove an error source, or the human error source, is something we're doing for them and for us and saving money. To truly see the value, though, we had to get to the stakeout. This is what changed the entire game. Everybody who's done stakeout with a GPS that's not got an IMU tilt compensation inside of it knows how tedious it can be. It's just like using a robot. It's in, out, a tenth, it's right, and you plumb it up, and then it's another couple hundreds here or there. Well, now you can just literally drive the tip of the rod to the point to stake it out. I had customers staking out buildings, houses, all these type of things, and they're doing it 2 to 3 times faster than what they were doing it before because of the GS18T. Again, the future-proof, just looking at that satellite constellation is a major difference and allows us to deliver a lot of these solutions. Our SmartCheck is a technology that goes way back, but it's still something that's as relative today as it was when it's created. You can get a bad initialization. Anybody who's used GPS long enough knows this. Well, what SmartCheck is doing is every 7 seconds, or about the length of time it takes to compute a new initialization, it is checking that to the existing initialization. So when you're out there working, changing environments, doing these things, it is comparing and recalculating on one part of the process or a new initialization and comparing it to the other one. It's a technology that Leica's had for a long time, but like I said, it's just as relative today, if not more so, as we try to push the boundaries and get the shots on that section corner deep into the woods and things of the like, now that we can begin to dream about pushing those boundaries that far. Our network correction service of SmartNet is the largest North American correction source or subscription service for corrections. We have 1,500 stations in all 50 states, and then in 8 provinces. Beyond that, we have the SmartLink, which is a satellite-based correction service. It's a precise point positioning where you subscribe to it. So it's ideal to either work in open areas that are very challenged for cellular coverage or weak or no. There's complications of having bases. Maybe you're in a highly magnetic area, things of the like that do disturb, or you have high iron core or something like that in the hills around you, and they will distort your radio signal. Well, having SmartLink or SmartLink or SmartConnect will allow you to bridge those gaps. So it allows you to take where you lose your cellular service or lose your RTK and bridge that until it comes back, or you can just have that as a standalone service and be running off of it. So I mentioned this earlier, but the self-learning GNSS really playing below the threshold of what is good. So having that signal to noise ratio, if you have 5 satellites that have, for instance, no signal to noise ratio, one north, south, east, and one straight above you, you've got really good geometry and you've got great signal. You could add 5 more satellites, northeast, southeast, south, and another one above you, and they all maybe had a little bit higher noise. Well, then they're actually even though they would be below the signal to noise ratio that would be considered good, they're not really bringing value to your measurement. So we can filter those out, or the GPS can learn, and it's checking these continuously, and it's just the speed of the process or the miniaturization of the technology and the ingenious of the guys running or writing the algorithms to be able to do these and filter out multipath and other things in real time. So we're also fully engaged in the ConX and the Leica Exchange, which are our cloud services for transferring data to and from the field. ConX is specifically around our construction side and our Icon software, but it's also available on our Leica Captivate. And that's because the surveyor is working in all those environments. He's part of that team, and he's part of the true survey side of the house, where, you know, many more construction sites, they have their own layout guys. They're using slightly different software. They don't really consider themselves surveyors, but many times you have a survey component that's giving them control, still checking some stuff. So now being able to work more closely with them is an advantage. Transferring stuff from field to office, office to field, or even surveyor to surveyor on site is just invaluable in increasing your efficiency and your return on investment. So we also offer our own training courses. This is something that all of our customers have access to, where they can go in, take the courses, they can earn badges, and it even comes with a quiz at the end, and there's testing, so you can use these for CEUs and you get certificates of completion. And this is to help them advance their learning and provide some additional value and help them with their continuing education requirements. So one of our things that one of our presidents, that we can create solutions only when we understand the problem. So we started to overcome some of this by allowing a tilt rover, that safety component, not having to get in the ditch, not having to attach a rod sideways, so you can try to plumb this pole as you measure these utilities in the ditch. But this is identifying the pain point or the problem. You know, demands time, it's just complicated to overcome, and it puts your surveyor inside the area of influence, inside the danger zone. So anytime we can do this, I heard them state this in the last presentation, anytime we can do anything to enhance the safety of our surveyors or our guys in construction or the people in the field, it's something we need to consider and look at. Getting survey grade accuracy under canopy. So we want RTK. It's the fastest tool. Anybody who's been to a bus depot knows that if they set up a robot, the bus is going to park right in front of them, guaranteed. So it's time consuming. There's ways to work around this using even the tilt rovers. You have to measure offsets and do some things. Again, you're introducing a time component. You're introducing a chance for human error to have erroneous measurements taking. So we're risking the compromising accuracy here. Another pain point is measuring single points or areas of rich detail, but maybe I don't need all of the detail, but I just don't know exactly what detail the engineer or the customer that I'm delivering this to, whether it's in-house or external, is going to need. What is this corner of the building? Is it the top facade, or is it the wood facade below? What do we need from these steps? Do we need to know just the rise and run so that we can put this on an ULTA to say that it meets a current building code, or do we actually need this dimensioned out for an addition or something else? Again, it either adds a time or a labor-intensive component to doing it without additional technology. So time saving, trading off completeness of an investigation or the like for the speed of clearing a scene. The reason this is so important, it's not that they're trying to rush through with their job, but the longer a scene goes uncleared, the higher the risk is for secondary and tertiary accidents to happen because of this. So the faster that they can safely and more completely clear this scene, the better off it will be for the whole populace that's affected by this. And that's all of us, no matter where we live. So we've got decades of innovation. We've talked a lot about the pain points, and now we'll reveal the solution. This is the GS18I. So this is a GS18T with visual positioning component. So it's a full tilt rover that adds a visual component to it. And because of the IMU, because of the RTK plus, we can now measure point or image groups and then extract single points from this. And this is not static photogrammetric, this is dynamic. So the sensor fusion for the survey grade accuracy is the full GNSS. We have to have an initialization from the GNSS. We have to have an IMU that's initialized. We combine that with the imaging sensor, and then we put that into the algorithms that allow us to merge that technology and quantify it and measure accurately from it. So imaging power is the sensor combined with our field software, and then that can be added for additional robustness to our office software. So literally, we want to imagine measuring what you can see and not what you can touch with your GPS. It is using a camera, it does have a field of view, and we can still collect, control, and any of the single discrete points we want, and even create checkpoints by measuring with the GNSS and then extracting that from the image groups and measuring those discrete measurements. We don't have to measure multiples by picking a single point, and we'll go into how it does this in a couple of minutes. But we can pick single points, and the system will go and find the same pixel in multiple image and compute the intersection and create the point there. We can bring that into the office. We use the same engine to create single points in a more comfortable environment, but we can also work from a dense point cloud created from the images. Or we can just have the dense point cloud there as the ability to realize the site in 3D and still extract those single measurements. So this point clouds are derived from images. They are not derived from LiDAR data, but it's very similar to what you could get from a lot of the drones and the other things out there. And it's a complementary technology. It's not a competitive technology. So the drones are still going to cover much larger of an area and they're still going to be a very specific place for them. But we can augment that. We can get the oblique images. We can get curb lines and things like that that you would never think of getting the rich detail from a drone. So how does this actually work? So we decide the object we want to capture. So in this, we saw the highlight of the corner of the building. We go and we capture an image group. So the GS sensor is moving. It has to have an RTK initialization, and it has to have the IMU initialized. So just movement will initialize the IMU. We go in and we pick the point in the center image or from the center of the image group that we want to digitize. And then the software will go through, it'll pick that same pixel in multiple images and will create the intersection. This is the hardest slide to get off of. There. So what does this actually look like in the sensor? So anybody who's seen the Leica RTC 360 scanner has probably seen something like this. So this is not Viz technology, because Viz technology in the RTC is being used to assist in positioning the actual scanner as it moves around. What we're doing in this case is using a subset of the Viz technology, but not to position the sensor, but to put the images from one to the next where it can have those distinct relative points that it helps pick from. When you pick the single pixel, it can go in, it finds these common points, aligns the images, and then picks that same pixel from a different image. So GNSS survey grade accuracy. So with regular RTK being network or base radio, you're looking at two-dimensional from 2 to 4 centimeters and 3D 3 to 5 centimeters. With the PPP and the SmartLink service, you're looking at 4 to 6 or 5 to 7 centimeters, 2D or 3D respectively. So we'll take another look at this sensor fusion for the survey grade. And for any photogrammetrist out there, you'll see that each image has its XYZ because it's tied to the RTK engine. And we also have the pitch, heave, and yaw of that image or of the camera, the sensor, so that we can project every pixel and then do the intersection. And that lets us calculate our actual point that we want to extract from the image. So again, we had the GS18T. It allowed us to overcome some of these measurements of not having to put somebody in the ditch or not having to have an offset rod. But now we can literally just walk down the ditch and choose to map either individual points, or we can create a point cloud of all the utilities that are in there. What does this look like in practice? So we go to our measure points from images. We choose an image group. It loads the image group. We move through the individual images until we have the object that we want to capture. We can zoom in, pan around. We choose to pick a single point in there. We tell it to measure. It's going to tell you how many points and give you a 3D or a 2D quality control. In the Office software, you can extract a 3D quality as well. So it's just that simple. Another pretty unique use case is measuring stockpiles. This is something commonly done with drones, but there's a ton of stockpiles out there that need to be measured. You literally just walk along at a normal pace. You can see the person walking on the left. This is what the camera's capturing on the right. It gives you your quality of your image group, the number of images, and then from that, in the office, we can create a dense point cloud, and we can very easily create a tin and contour that. So this is Leica Infinity. This is our office software. Simply name it. And apply it, and then we can create contours on it as well. Once we have that, we can do some simple reporting right in the software as well to do volumes and whatnot. So one of the main things that come is how accurate and where does the rubber meet the road. So I know these are kind of small, but you can see where we've got door 03 and door 04 up there. These are 2 points picked from the images. Here we're looking at the 3D viewer. We pick those 2 points and we compute an inverse. I do apologize for these being in metric. I got these from a colleague in the UK, and you'd be surprised at how hard it is or how time consuming to put some of these presentations together. So I am borrowing some of this from him. We have done our own tests, but putting it in a pretty format is time consuming. So, but you can see that our slope distance here between those 2 points is 0.785 meters. What does that really mean? Well, right there, you're talking millimeters, if that, for our relative accuracy of measuring from the points picked to actually slapping a tape measure up there and extracting the measurement or verifying the measurement. Now, not every measurement out there, anybody who's done anything with any photogrammetric measurements is not expecting to get millimeter accuracy, but it can be done. And you can see in this case, and actually in a lot of cases, the relative accuracy is outstanding. It's only in the absolute position that we start to see that 3 to 5 centimeters if you use good practices, and that's with everything in surveying. So again, we did the bottom of the door, and we can just show that it can be repeated again within a couple of millimeters. So this just walks through and highlights a lot of our technology and the different challenges you might face. So this is a non-tilt compensating rover, and you can see everything highlighted in red here would produce some type of challenge for a non-tilt compensating rover. You can see that that red area pulls back a little bit when we add a tilt compensating rover. Some of the smaller trees become non-challenged, but some of the bigger ones still were. And of course, we have the overhangs and stuff that can't be overcome with GPS. Then we go to the imaging, and there's nothing on this site that we can't get by using the imaging rover. And this is only due to the capability of synchronizing that with the IMU and with the GPS. So with that, I don't know where I'm at on time, but we are ready to take some questions.
Cool. Thanks a lot, Bob. You got about 13 minutes left. And yeah, so some folks that couldn't stick around had sent me some questions by email, and they're surveyors. So I think you can anticipate what those questions might be. But a comment on this, I have not tried the I model yet. You know, the GS18T, my test series. On one of them, I showed my daughter, who was in high school at the time, how to use it in about 2 minutes. And her comment was, and you guys get paid this much to do this? As run around. But no, but she was kidding. She said, yeah, well, I understand that you have to assure how precise that is. And that's the key. So can you comment a little bit on how deep can somebody go into the data to look at the quality with the eye as well? I mean, if you got, you know, we're all used to looking at PDOP and residuals in GNSS, but in the tilt in the image, what kind of quality indicators or data can someone dig into?
There's quite a bit embedded into the software, so we can see the full pitch, heave, and roll component of the IMU is reported at all times. And our QC values, so the QC values displayed on the rover are always taken into account with the T model. Any error that comes in, you add another sensor, you add error. That's a fact, right? There's just nothing anybody can do about that. But what we found was there was more error in the bubble, because anybody who's held a rod steady and taken a measurement at 2 meters, even inside the black bubble or just out at 2 meters high, that's a centimeter or two. So hold that steady for that long, especially, we all love to carry bipods, right? They're just wonderful to carry a bipod when you're doing a topo or you're doing something of that sort. So that's where you can take an instantaneous measurement and you're more accurate than what you can hold that rod. And there's nothing replacing a static measurement, or even better than that is multiple measurements. We say 6 hours apart, but in reality now with 29 potential satellites, even 15 or 20 minutes, if you come back, your geometry has changed a lot with the number of satellites, that if you take redundant measurements and average those, that's where you're really starting to look at your accuracy component or being able to check that. But we do report on all of the IMU status along the way. And what we're doing with the image group, and we give you that image group quality, is we're tracking 30 points continuously. Now the points are constantly moving, and we're doing intersections to all those 30 points in the background. Now, one thing I might not have stated here is we do have a range, or the object has to be in a certain range. So we need to be collecting an object that's between 2 and 10 meters. So that's 6 to 30 feet.
Okay. That's
so,
the question, yeah.
Yeah, so with a moving IMU, that lets in the pictures in the position from the RTK, that lets us create those intersections. And you can manually go check those, and you can manually go add more points to them. So the algorithm, we're still smarter than the computer. I know most people don't believe that, but we are, because the algorithm is only so robust, or the computer is only so powerful. And we know instantaneously, if I go around a corner, if I go further around that image group and pick, I've just increased my geometry. So I've just strengthened my figure to that point, right? So if I take three on a flat plane and pick from the middle one, it's only going to go out so far. But if I know I walked around the corner, if I put another bearing in there, that's going to increase my strength of figure.
Oh, okay. So if you are walking in front of a long building, it might behoove you to do a bit of a tack in your walk.
Absolutely. Do a little tack in your walk, and at the end of the building, if you want to round it a little bit, there's some subtle things like that that are part of our best practice, right? That we would explain and work with our customers as we're introducing this technology.
Okay, we have a question here from Hector C. He says, can this GNSS receiver be used on a backpack with the same data quality?
Actually, yes, because we don't care where the receiver, you have to have the data collector, but the receiver can be anywhere. Now, the caveat to that is even on a backpack, your image groups can't be more than 60 seconds long. Now, you can take a lot of image groups, but a single group is restricted to 60 seconds, and that's solely a restriction on the mobile computing power to process that and process all those images together and package them and store them. So you can collect as many image groups as you want, and it doesn't matter if it's on a backpack. It doesn't matter if the rod height is 1.5 meters or 2 meters. That's all that matters is you have an RTK initialization and that you have your IMU initialized when you start capturing your image group.
Okay, so when you do an image group, you have to intervene. You have to pick a point in there, right?
You don't have to. You can wait until later. You've digitized the whole thing. Once you've captured the image group, you can go and extract anything you want from inside of there. And it gives you the quality of that image group is what you should expect from any single point you go to digitize. Now, you can digitize those points in the field in the office. So if you need to know an offset of a roof line to a property line because you're reserting a house for an offset, well, then you can just simply digitize that, compute the inverse in the field, right?
Okay.
If I have a bunch of asphalt or a bunch of utility lines or something else that I just want to walk next to, and then I want to beat this rainstorm and I want to go extract the feature lines for those and create those in the office, then I can do that there as well. And then the only place I can create a dense point cloud is in the office.
Okay. Well, I can see where somebody might be going with this notion that if your image groups are 60 seconds maximum, you could, I mean, does it end automatically at the end of 60
seconds? It does. Well, it will end and then it'll come up and give you a QC value. You can hit store and then you can instantly hit start measuring the next one.
Okay.
So you can just pause for a minute, store that one, and then continue on.
Oop, we lost you, Bob.
I'm still here.
Oh, you're back. Okay.
Okay.
So you could, if you're, you're walking around a large structure or something, doing a ALTA survey or whatever, you could hit the 60 seconds, hit it again. Of course, the question is, there's got to be a limit to storage, though, or can you stick a gigantic SD card in the unit?
You can stick a gigantic SD card in the unit. The onboard memory of both the CS35, which is the Panasonic Tough Pad, or the CS20, both have a lot of internal storage. So it's not, I mean, years of data, months of data. If you're doing this all day, every day, you need to clean off your jobs. But on a single job, we spent 4 days collecting nothing but data from dusk till dawn when we first got this, and we never had a storage problem.
So it's storing on the data collector?
On the data collector. Yep.
Okay, not on the rover head. Okay.
It logs them in there, and when you stop storing it, it transfers down from the receiver head with all the pitch, even roll, all the metadata.
Oh, okay.
Every image, it transfers it to the data collector at that part.
Is that by Bluetooth or Wi-Fi?
That's by Wi-Fi now. That's what makes it fast enough. So we were talking with the AT&T Bluetooth. Now with this latest generation, the connection to either the T or the I can be with a Wi-Fi.
Okay, great.
WLAN actually.
But. Yeah, moving that amount of data that fast could be hazardous.
Exactly.
And there's another question somebody asked me to ask. They're trying to figure out what the absolute value of that point is distant. Because there's applications where the relative, you want the absolute rather than the relative. And, specifically, sometimes, we can't enter somebody's property. We have to stand on the right of way and try to get the building corner. So following what they asked was, okay, say you've got a centimeter, you know, let's say you've got great RTK, you've got a centimeter there, and you're not tilting very far, so your tilt's another centimeter maybe. And then you got your 3 to 5, okay, you're 10 meters out. What would it be at 10 meters out? Compounding those.
That's the absolute is you're looking at 3 to 5 centimeters.
Oh, okay.
So that's combined with all the sensor. And many times we did a parking lot. And actually, if you'll notice on the screen, the peer surveying website, I have another webinar coming up on the 17th that you can find out more there. But I will be showing an application where I did a parking lot for an Alta survey example, and I did a building for the same thing. And I'm hitting my control. You can see it on the point cloud, you can see it other ways, and I'm hitting it within a tenth. And most of the time, that's a couple centimeters, probably closer to 3, and that is mostly in the vertical component, as you would expect.
Okay, well, you know, I've just been out with my total station, freshening up my test course and adding points on some buildings. So, you know, I'm going to put it through its paces. So
I'm working on getting you one. I can't wait.
Okay, looking forward to it. Thanks a lot, Bob. Really appreciate it. And I have to mention that Hexagon is one of the sponsors of this and so far all of the events. And so we gave a little leeway on going through your product catalog, but you know, Hexagon's always been a great sponsor of these things. So we're going to move on to, I hope people stick around for the final session because